for this next problem, we're going to find the work that a hiker has to do on a 15-kilogram backpack in order to carry it up a hill that's 10 meters tall at constant velocity. So I have a couple different diagrams for you here. This is the free body diagram of just the backpack itself. Okay, if it's moving at constant velocity, he's not really lifting it. He's exerting just enough force basically to keep himself upright and to keep the backpack at that location. Okay, so here's our free body diagram of the backpack itself. This over here is just basically showing the initial position of the backpack as compared to where it will end up after he's done hiking. Okay, these forces right here, are they vertical or horizontal? Vertical, which means we only care about which displacement, the vertical or the horizontal. Vertical displacement. We don't care the total distance that he traveled, the hypotenuse of this triangle. All we care about is the vertical distance that the vertical displacement that he underwent. Okay, he started at this place down at the bottom of the hill, and eventually he ended up 10 meters above where he started. That's all we care about. We don't care about the actual number of steps he took or the actual distance he walked. We care about the displacement where he is above from where he started. Okay, so this height here will really be our displacement for our problem. All right, because we're going to have vertical forces, which means we only care about our vertical displacement. Okay, we've got two forces acting on our backpack here, one of the hiker and one of gravity that's pulling that backpack down. All right, so let's go ahead and solve first for the work done by the hiker. You could label this just work sub H or whatever you want to do. You don't have to write out hiker. We'll take force of the hiker times displacement times cosine of theta. How do we solve for the force by the hiker?
Gravity times the weight.
Yeah, yeah. Why can we make that the force of the hiker?
Because gravity flows. It's moving at constant, so it's the same.
Exactly. Since it's moving at constant velocity, these two forces must be the same. Okay, he must be just doing enough to keep that in balance. Okay, so that means our force on the hiker is going to equal F sub g, which is 15 kilograms times 9.8. Good, which is 147 newtons. Okay, now we're going to take our work done by the hiker as 147 times 10 meters. And do we have any theta here that we have to work with? They're already parallel. Okay. Already parallel. So we'll just do cosine of 0, which is just 1. Okay, which means we're at 1470 joules here. Okay, and the work done by the hiker, is that going to be positive or negative? Positive, because it's holding it up. Very good. Okay. Now work done by gravity will be pretty much the exact same thing, right? Because our force due to gravity is the same, just in the opposite direction. So our force for gravity is negative 147 times 10 meters. It's still going upward 10 meters, so our displacement is still positive 10. Okay, so if our work done by the hiker is 1,470 joules, and the work done by friction is negative 1,470 joules, what's our overall net work? 0 joules.
Wait, how do you do the work due to gravity?
We're going to just take our force due to gravity, which is 15 times 9.8, but since it's going in the negative direction, we're just plugging in the negative 147 newtons. Okay. We could have solved this a little quicker by just seeing that the net force of this system was 0. Right? You guys saw that it's moving at constant velocity, which means you know the net force is 0. That means the work done is 0. Okay, does that make sense? If you can see that part of it a little quicker, that's going to speed up the process of your solving. Yeah, energy is in every single science all the time. That's the basis of everything here. Okay? we're going to look at two main types of energy. There's a lot of different ones. We're going to look at two different types of energy called translational kinetic and translational potential energy. Okay, kinetic and potential energy are going to be our two types that we're going to talk about here. What's it mean to be translational? Yeah, good. Translational just means it's not spinning. It's moving from point A to point B without rotating at all. Okay, so we just finished our chapter on rotational motion. Now we're done with all that radians per second stuff. We're back to meters per second for our velocities, things like that. We're just looking at things that move from point A to point B in a certain amount of time. Okay. Energy in your physics terms now becomes the ability to do work. Okay, it has enough energy in order to complete this task. It has enough force being applied over a certain distance to do work or have work done to this object. Okay, so that's what energy's basic definition in physics is, the ability to do work. Okay, we're going to first talk about kinetic energy. Okay, I should have asked you this before I put it up there, but kinetic energy means it's the energy of something in motion. Okay, kinematics, we did all of our kinematics equations. Those are things in motion. Now, kinetic energy means the object, the energy of anything that's in motion currently. Okay. Something that we're going to focus on a lot here is the transfer of kinetic energy from one object to another. Whether it be in collisions, whether it be in applied forces, things like that, you can transfer kinetic energy from something to another thing. Okay. So this paragraph is a little bit long-winded, I guess, for what it needs to be saying, but when a force is exerted on another object and that second object travels a distance, that means work has been done. I've transferred kinetic energy, which means there's been work that has been done. Okay? Kinetic energy, this is the equation that we use. Ke equals 1/2 mv squared. So kinetic energy has to do with mass and velocity. What other term or what other system or equation do we know that has to do with mass and velocity? All right, this is translational kinetic energy, things that are not rotating. Okay, things that are not spinning, don't have a rotational motion of any kind. They're just moving from one point to another. No. Sorry. Okay, so now let's go ahead and connect work to kinetic energy. I told you when I put something in motion by transferring kinetic energy, I exert or I do work on that object. Now we can connect these two with an equation. Okay, so net work is equal to change in kinetic energy. Remember, delta means final minus initial. You can replace this 2 and the 1 if you'd like with an F and an I. If you want for final and initial, it doesn't make a difference at all. Okay. What this equation is saying here is that net work is equal to 1/2 m times velocity final squared minus 1/2 m velocity initial squared. Okay, and all I did here was plug in this kinetic energy equation. End up using it, but you can see it both ways. This right here, this net work equals change in kinetic energy, is called the work energy principle. That's something that you'll have to know. Okay, that work energy principle equals work net equals delta KE. Okay. All I did with that was plug in mv squared, you know what I'm saying? Because this equation right here is the one below it. Okay, so that's all I did. Okay, this work energy principle only works for net work, so you can't plug this in for frictional work or applied work or whatever. It's got to be the net overall work of the system. Okay, that's the only way that it will be correct. Okay, so these are some relationships that I want you to listen to and think about for this work energy principle. Okay, not necessarily things you have to have in your notes, but I do want you to understand the connection between them. Okay, so work energy principle tells us that if positive net work is done, then the kinetic energy increases. Okay, if positive work is done, then kinetic energy increases. So think about when I pushed that binder. Did I give it some motion? Right? Was its final kinetic energy greater than its initial kinetic energy? Yeah, because it started from rest. Okay, and let's pretend that it didn't go to rest. It just kept going like it was supposed to. Okay, so I gave that energy, which means I did positive work on that object. The same is true in the reverse. So if negative work is done on an object, then its kinetic energy decreases. And if no work is done, then its kinetic energy remains the same. Okay, so I want you to just think about the relationship between these two principles. No direction. Okay, so kinetic energy is measured in joules, and it has no direction. So there's no kinetic energy in the east or west or any of that. All right, let's go ahead and try one here. 145-gram baseballs thrown with a speed of 25 meters per second. What's its kinetic energy? And then for the second part, we say how much work was done to make it reach this speed if it started from rest. Mass in grams to mass in kilograms. So to convert from grams to kilograms, we move that decimal place 3 to the left. Okay, so the first part of our question asks, what is the kinetic energy? That's going to be our first goal here, is just using this equation to solve 1/2 mv squared. What did we get for our kinetic energy? 45? 44 point something? 45. Okay. 45.3. And what's our units? Joules. Good. Joules. Okay, so now it asks how much work was done on the ball to make it reach the speed if it started from rest. So if it started from rest, that means its initial kinetic energy was 0, right? If it had no velocity at the beginning, that means it had no kinetic energy. So when we're solving for work, we're going to look at net work equals delta KE. So net work equals 45.3 joules minus 0 joules. Okay, since this was our final kinetic energy, our initial was 0, we said because it started with no velocity. So that means our net work is 45.3, also in joules. We had positive net work, which shows we had an increase in kinetic energy, which is exactly what happened. Okay, that ball started from rest. It ended with an increase in velocity, which means we had an increase in kinetic energy, which means we had positive work. Let's try this last one on your own. I'll be doing it up on the board if you have questions, but we're not going to talk through it as a class. positive work or negative work? Positive work. Okay, and we had an increase in kinetic energy, is that right? Yeah, because we had an increase in speed. Okay, so positive network. We could have solved each of these separately, solve for kinetic energy final and solve for kinetic energy initial, and then plugged them in, but I just went ahead and used one equation. Okay, you can do that either way. Okay, so your homework, I'm going to go ahead and write it up here on the board. Okay, so on number 3, you only have to do A and B. On number 8, you only have to do A.